Hello, I'm Matt Walker, and this is my new hire talk. So I just started with the Planetary Science Institute sometime in February. So I guess I'm pretty new here. I'm using this talk to help promote my work and to find people to work with at PSI. So here's my email. Please message me if any of this is interesting to you, because there's probably so many things we can work on together. Next. So I've broken this up into sort of three sort of themes. So I study tides and tidal deformation. So I'm going to talk about tides first. I'll move into deformation and how the tides deform stuff. And then finally, the thermal evolution, which is what I'll focus on the most. Next. And I applied this stuff to icy satellites, mostly ocean worlds. And I've got a list of them here. Europa and Enceladus are the classic ones. But I'm interested in trying to put this stuff on Mercury, Venus, exoplanets and such, anything that's really got weird spins or orbits, obliquities, because those have very interesting tides. Next. So what is the tide? The tide is just a bunch of geometry. So I do a bunch of geometry and I include all sorts of things in my tide. So a standard tide is mostly an eccentricity tide, but I'm looking at obliquity tides too. I do lots of non and not synchronous rotations. Forced libration is a new one I've been looking at, which does some interesting things. I'm starting to get into spin pole precession and true polar wander as well. Next. So when I do all that geometry and all that math, it ends up in this nice compact form, which is sort of intimidating, but it's mostly combinatoric, so it's not too bad. But if you do anything with tides, you maybe want to message me to look at this equation with me, because it's fairly simple and straightforward to use. And what it captures is all the frequencies that show up in a tide. Next. And why do I care about the frequencies? I care about the frequencies because the deformation that happens as a result of the tide, if you're doing viscoelastic deformation, it's extremely frequency dependent. So typically we look at displacements, strains, stresses, and I kind of focus on the tidal heating. And if you look at these plots to the right, you'll see those blue curves. The blue curves represent tidal heating for a Maxwell rheology at the top and an Andrade rheology at the bottom. And those gold curves are sort of like stress. So you see that peak right at about 250-ish Kelvin. And that is the peak heating. And that's going to occur right near these ice shell bases. But I said the frequency is important. And the frequency is important because, this is for Europa. But if you had a faster beat, you're going to shift that peak to the right. If you have a slower beat, you're going to shift that peak to the left. So what we're saying is that heating, the position of the heating radially in the ice is going to change based on what frequency in the tide you're looking at. Next. So tidal heating, right? This is my pretty tidal heating pattern. This is a 10-kilometer Europa, so fairly thin shell. You probably can't see that this is only about 1 milliwatt here per meter squared. So it's a low flux, and that happens because it's a pretty thin shell. So this is just a typical tidal heating pattern. I just thought I'd show it because it's a nice picture. Next. And this is what I do with that tidal heating pattern. That Q is and I've circled it in red there, that Q is the source term, the tidal heating source term for my conduction differential equation here. So what we do is we solve for the temperature, and then that temperature, we also take the gradient of that temperature to get the heat flux. So we run this thing to steady state, look at the temperatures and the heat fluxes, and what we're seeing is that this source term makes a huge difference to the equilibrium temperature and flux profiles. The gold dots on this plot represent the surface heat flux, and the blue dots represent a basal heat flux for a bunch of different ice shells, a bunch of different Europa ice shells of varying thicknesses. And I picked the average location, so the average tide strength here. And to the left of this plot, the very thin shells, you'll notice that the blue and gold dots sit almost on top of each other. What that's saying is there's not a whole lot of tidal heating going on in these thin shells. But over on the right side, where there's a kind of a big wide gap between the blue and gold dots, there's a very strong tidal heating. And up to about 33.5 kilometers, that's the thickest Europa ice shell I think you're gonna find for an average Europa ice shell thickness. And why that happens is because you see that the dots are getting far away from each other, and what we're getting is that if you go any thicker than that, the thing starts melting from the inside. So it's super cool. I call this thing a zipper plot, and I love making them. And as the forcing changes, those blue and gold dots kind of zip in and out of, into and out of each other. Very cool stuff. Next. So what do I do with this? I'm working on a couple projects here, and the first one I started working on was this solar system workings project with Alyssa Roden. So we've been looking at how the Europa's ice shell is going to evolve and how the surface morphology that results from it. And we're looking at how variable forcings can thicken and thin the shell over very long time periods. And recently, we're including things like thermal stress as well, where the actual thickening and thinning of that shell due to phase changes in the water causes thermal stresses, which can, in some cases, penetrate through to the oceans. So we can't get it to happen on Europa, but we've been seeing that for Enceladus with lower gravity, you can in fact get these cracks to penetrate to the ocean, which is extremely encouraging and exciting. Next. And another project which I've been involved with is this Signals Through the Ice project with Kate Kraft out of Johns Hopkins Applied Physics Lab. And this is very cool. This is tethered cryobots. And what we're looking to do is see how viable this type of technology is. So there's people on the team who are doing lab experiments to fabricate tethers and then shear them in ice, like you can see on the bottom there. And my role in this project is to inform the environments and the types of stresses and strains that these tethers will need to withstand at all locations and depths in the ice. Next. And right after I got to PSI, we were awarded this Cold Tech, which is an extension of the project where we can actually start developing better prototypes. So super grateful to have been involved with this and look forward to finding the tethers that we can get to survive. Next. And even though I'm new, I've already put in a CDAP. We just put this in just a month ago, right? And what we're doing with this is we're looking how impacts trigger enhanced tidal heating. So what happens is there's a rheological resonance that happens when an impact increases the surface ice temperature. And by increasing the surface ice temperature due to an impact like this, we see a ton of extra heating and a much different heat and flux profile. So we're going to see if we can do that. We're going to see if we can do something like this to explain the high viscous relaxation we see on the ice shells in the Saturn system. Next. So my preliminary work was mostly Europa. So this is an example of what happens when you smack a Europa with an impactor, and you see that blue temperature profile here. That very hot surface stuff is my proxy for an impact. And the green line and the gold line are very different. Those are both steady state, green with an impact, gold without it. And what happens is a tremendous difference, especially in the flux profile. You see that surface flux is very high, and that's a steady state. So it's super high steady state heat flux. And we think something like this applied to the Saturn system can explain the high viscous relaxation in those craters. So can't wait to start working on that thing. Next. And the reason it happens is just because there's this rheological resonance. Once you get any ice hot for any reason, once you get these ices hot, you're at the right frequency and you're triggering that enhanced heating. So next. So I got to thank a bunch of people, my red team, and a bunch of people for invigorating conversations, and especially Kelly and Elaine. Thank you so much for getting me through my first submission. Next, and here's my email. Please message me.